Hello and welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be covering our third honors topic, Gibbs free energy. Our aim for today is, how can we use Gibbs free energy to determine the spontaneity of a chemical reaction? First, some notes about Gibbs free energy. Gibbs free energy is the maximum amount of energy that can be coupled to another process to do useful work. For our purposes for today, we care about this formula. Delta G, change in G, Gibbs free energy, is equal to delta H, heat of reaction or enthalpy, minus T, temperature, times delta S or entropy. So delta H, that's enthalpy, heat of reaction, and S is entropy, the measure of randomness or chaos. Some notes: if delta G is negative, the forward reaction is spontaneous. So after our calculations, if this value is a negative delta G, that is going to be spontaneous. The opposite is true as well. If delta G is positive after performing this calculation, that means the reaction is spontaneous in the reverse reaction. So if delta G is positive, it is not spontaneous as written. You would have to reverse the reaction, and that would be spontaneous. It is named after American scientist Josiah Willard Gibbs. Here on this data table, we see different conditions in which a chemical reaction will either be spontaneous or non-spontaneous. So the first column, we have delta H, which is enthalpy. And in the second column, we have delta S, which is entropy. Once again, delta H, heat of reaction. Delta S, change in randomness, change in the amount of chaos or disorder, that is entropy. So, under our first set of conditions, if we have a negative delta H and a positive delta S, that means you will always have a spontaneous chemical reaction. That means if the reaction is negative, it's exothermic, it's releasing energy, and delta S is positive, becoming more random, so exothermic and more random, that is always going to be spontaneous. And the opposite is true as well. If we have a positive delta H and a negative delta S, that is always going to be a non-spontaneous chemical reaction. So that being said, positive delta H would be endothermic, negative delta S would be becoming less chaotic, less disordered, or more ordered, and that would never be spontaneous, not at any temperature. It'll always be non-spontaneous. Now these other two situations, that's where the Gibbs free energy calculation comes in. If we have a negative delta H, which is what we want for a spontaneous reaction, an exothermic reaction, but a negative delta S becoming less disordered, it depends. So it'll be spontaneous at low temperatures, but non-spontaneous at high temperatures. And once again, the opposite is true as well. If we have an endothermic reaction, what we don't want for a spontaneous reaction, and a positive delta S, so more chaos, which is what normally does happen in a spontaneous chemical reaction, it'll be non-spontaneous at low temperatures and spontaneous at high temperatures. Why? High temperatures favor the entropy term because it's T times delta S, and low temperatures favor the enthalpy term. Let's do a couple practice problems. Let's try practice problem number 1 together. Problem number 1 states, for the reaction, carbon monoxide, CO gas, plus water vapor, H2O gas, yields CO2, carbon dioxide gas, plus H2, hydrogen gas. Then it gives us the parameters. Delta H is negative 41.2 kilojoules, and our delta S is negative 135 joules per Kelvin. For letter A, it says calculate delta G at room temperature, which is 298 Kelvin. The very first thing we're going to do is we're going to write our formula. Delta G is equal to delta H minus T for temperature times delta S. But before we start plugging in numbers, we have a problem with our units. For delta H, our units are in kilojoules, whereas for delta S, we have negative 135 joules per Kelvin. We need to make sure that these units are the same. The easiest way to do that would be to divide the negative 135 joules per Kelvin by 1,000. The reason for that is there are 1,000 joules in 1 kilojoule. If you look on table C of your chemistry reference tables and look at kilo, you will find that the factor for kilo is 10 to the third. There are 10 to the third joules in 1 kilojoule. 10 to the third, of course, is 1,000. So when we divide negative 135 by 1,000, we get negative 0.135 kilojoules per Kelvin. Now we can plug numbers in. So we have delta G is equal to delta H, which is negative 41.2 kilojoules, minus, I like to put this part, the T delta S, in parentheses, open parenthesis, 298 Kelvin times negative 0.135 kilojoules per Kelvin, close parentheses. Now we can start solving. Delta G is equal to negative 41.2 kilojoules minus, now let's multiply inside. We have 298 times a negative 0.135. So we get inside the parentheses a negative 40.23. For the units, notice Kelvin and Kelvin cancel out, so we're left with the unit of kilojoules. Now before we go any further, we have negative 41.2 kilojoules minus a negative 40.23 kilojoules. These two negatives, this double negative, cancels out and becomes a positive. So now, to finish this off, we have negative 41.2 kilojoules plus a positive 40.23 kilojoules. That is going to give us a delta G value of negative 0.97 kilojoules. And remember from the previous slide, if you have a delta G value that is negative, that means the reaction is spontaneous as it is written. For problem 1b, it says calculate delta G at 700 Kelvin, assuming that delta H and delta S are temperature independent. That means the delta H and the delta S are going to stay the same. The only thing that we change is our temperature. So once again, we write our equation. Delta G equals delta H minus T delta S. We plug in our numbers. So delta G is equal to delta H, which is still negative 41.2 kilojoules, minus, let's open up the parentheses once again, put the now 700 Kelvin in there times, once again, negative 0.135 kilojoules per Kelvin. Close parentheses. So now we can start solving again. Delta G is equal to negative 41.2 kilojoules minus, open parentheses, we have 700 Kelvin times negative 0.135 kilojoules per Kelvin. So we get a negative 94.5, and once again, Kelvin and Kelvin cancel out. We're left with the unit of kilojoules. Close parentheses. Once again, inside the parentheses, we have a negative value. We're subtracting a negative. Two negatives make a positive. So we'll change those to positives. So now we're left with negative 41.2 plus a positive 94.5 kilojoules. That's going to give us a delta G value of positive 53.3 kilojoules. Also, remember from the last slide that a positive delta G value means the reaction is non-spontaneous. As written. So for letter C, does raising the temperature favor this reaction as written? The answer is no. And the reason why, at the lower temperature, 298 Kelvin, that gave us a delta G value of negative 0.97 kilojoules. That negative value means that the reaction is spontaneous. However, when we raise the temperature to 700 Kelvin, that gave us a delta G value of positive 53.3 kilojoules. The positive value telling us that this reaction is non-spontaneous. So, does raising the temperature favor this reaction as written? No. At the lower temperature, which was 298 Kelvin, the reaction was spontaneous. And at the higher temperature, which was 700 Kelvin, the reaction was non-spontaneous. And finally, we have question 2, which is a two-part question. Question 2 states, calculate delta G using the formula delta G equals delta H minus T delta S. Also, determine whether the reaction will be spontaneous at standard temperature, 273 Kelvin. Letter A, CH3OH liquid plus 1.5 moles of O2 gas goes to CO2 gas plus 2 moles of H2O gas. So for the first problem, we write our equation, delta G equals delta H minus T times delta S. But before we plug in numbers, we have the same issue as we did on the last problem. We have kilojoules for delta H, and we have joules per Kelvin for delta S. So once again, we are going to divide the joules by 1,000 so we could convert joules to kilojoules. So our delta S is going to be positive 0.1569 kilojoules per Kelvin. Now we can plug numbers in. Delta G equals delta S negative 638.4 kilojoules minus, open parentheses, temperature 273 Kelvin times delta S 0.1569 kilojoules per Kelvin. Close parentheses. Notice the Kelvin and Kelvin cancel out, so we're left with kilojoules. I would next, let's rewrite it, then we'll multiply delta G equals negative 638.4 kilojoules minus, let's do 273 times 0.1569, and that's going to give us a long answer, 42.8337 kilojoules, and we'll do significant figures at the very end. So now notice, I have a negative 638.4 kilojoules minus a positive in here now, 42.8337 kilojoules. So now I have the negative minus the positive. So let's do that. I have negative 638.4 kilojoules minus 42.8337 kilojoules. So our delta G before significant figures is going to be negative 681.2337 kilojoules. And if we look at significant figures, we have 4 significant figures, 4 and 3, so we round to 3. 1, 2, 3. 2 is lower than 5, so our delta G is negative 681 kilojoules. Since delta G is negative, that means letter A will be spontaneous. For letter B, we have 2 moles of NO2 gas goes to N2O4 gas. Here's our conditions, negative 57.2 kilojoules, and our delta S, 175.9 joules per Kelvin. Let's write our formula. Delta G equals delta H minus T delta S. And once again, we have kilojoules and we have joules per Kelvin. So we're going to divide by 1,000 to convert joules to kilojoules. So we get our delta S is positive 0.1759 kilojoules per Kelvin. We plug in our numbers. Delta G equals delta H, that's negative 57.2 kilojoules, minus, open parentheses, we have once again 273 Kelvin times 0.1759 kilojoules per Kelvin. Kelvin and Kelvin cancel out. Let's rewrite before we do any calculations. Delta G equals negative 57.2 kilojoules minus, open parentheses, let's do 273 times 0.1759, and that'll give us 48.0207 kilojoules. Inside the parentheses is positive, so we just subtract across. So we have negative 57.2 minus 48.0207, and that gives us delta G equals negative 105.2207 kilojoules, And if we round to significant figures, once again, 3 significant figures, 105. 2 is lower than 5, so our delta G final answer is negative 105 kilojoules. Once again, our negative 105 gives us a spontaneous chemical reaction. Thank you for joining Mr. Alvarez's virtual chemistry classroom. Today we learned how to use the Gibbs free energy equation. We learned that a negative delta G value means that the reaction will occur spontaneously as written, whereas a positive delta G value means that the reaction is non-spontaneous. It will not occur spontaneously as written. Thank you again for joining us. I hope you learned something today. Please join us again soon.